back to the second tutorial. This time we're going more into details with the source code. In the first tutorial we were talking about what could be changed in the XML files, and now we dive deeper into the source code. Here's a quick overview about the things we go through. First, again, some requirements. Then we will together set up OpenDS, the source code of OpenDS, to integrated development environment. And I have prepared some source code examples, some rather basic examples. So I hope you can follow, even if you're not an expert in game development. And at the end of the session, we'll learn something about how to establish a connection to OpenDS in order to grab data such as speed and other values live from the running system. The requirements for implementers are almost the same. The only difference is the last entry of this table, that you now need the Java development kit. Here, this is a requirement from the JMonkey engine. You need at least version 6 or higher. And you should have some experience with Java. If not already done, you can download the tutorial package from our website. And this time we will concentrate on the source code subfolder, which is contained here. For the people here in the room, I will show you what to do. You have this header on your USB flash drive in front of you, and we can do this now together. I try to guide you. We are going back to where we have stored these folders on our hard disk drive. We go to the software, and this time we need the assets folder that we moved to the binaries for the first tutorial. We need this asset folder now in the sources folder. So I just go there and cut it out here, as we now need it at that position. So one more time. It needs to go from the binaries folder. We go into the binaries folder. There the assets before. I cut
and go up and down into the sources, and I paste it here. Okay, I think this should not be that hard to follow. In the next step, we're going to import this source code project into Eclipse. So maybe some of you are using NetBeans or other editors. I'm just going to demonstrate it with Eclipse here. Does everybody have installed such a tool? Okay. So I run Eclipse from my computer. I think it's not the newest version. Yes. You don't even need the EE version. So if you started for the very first time, it looks somehow like that. We can skip the welcome message, and it's our working space. Everything is rather empty. So I just click on File, Import, and there's a list of what I can import, and just want to import an existing project into my workspace. So we can now select the root folder, and this is the sources. Okay, I don't check this box here, copy files into my workspace, as this would take too much time. So it's just linked. Yes, please. Okay. Let's see what happens here. It seems to work. Yeah. Here it seems to work perfectly. It would be fine if you could run this simulator as Java application. I tried to do this. Yeah, here it works. So I was also compiling did you make sure that you have installed the JDK? Maybe you just your Java version might be trying to run any precompiled any build files. So this might cause this class error. So yeah, you can see now this time I'm running the simulator from the source code. The result is exactly the same. So we can quit this as this is currently not relevant for the upcoming tutorial. So let's get back to the slides. We keep the editor open as we will need it for some examples later on. First, let me explain some concepts of the JMonkey engine. The first one is about the 3D coordinate space. So in JMonkey engine, we have a right-handed coordinate system. As I mentioned before, the x-axis is oriented from left to right. So values are getting bigger the more you get to the right. The y-axis starts below and goes up. So the higher something is placed, the larger is the y value, and the z-axis starts away from you and is going towards you. So here's an example: 0.3 minus 5 and 1 means you go 3 steps to the right, 5 steps down, and 1 towards you. The next is a rather interesting presentation. This is where you can find some other demonstrations as well. I just considered to show you this, which can be found on the JMonkey website. So it's quite nice and shows clearly about the scene graph. I think I can also show it in full screen mode. Yes. Okay. So this is just a quick guide about scene graph and what is the difference between geometry nodes and how you can organize a scene graph in the JMonkey engine using nodes and geometry as leads. Yeah, I think we can go over that. As I already mentioned, a right-handed coordinate system. And they have very nice examples. They assume to start with a spatial. A spatial is any object. Spatial can be even a node where you can group several objects to one super object. And they place it in the origin for that example with 0 location and 0 rotation. Assume it looks like that. Now they show how to transform this object, moving it, scaling it, and rotating it. And in this way, you will learn what methods you could use when you're confronted with the Java code of spatials. For example, you could apply method move with the x, y, and z coordinates like specified here. So you add one to the x-axis and one to the y-axis, which will result in something like that. You can also rotate objects around the z-axis. The z-axis is the one that is facing towards you. So rotating here will make this monkey face turn to left or to the right. Scaling makes it bigger. And now they're going to talk about the geometry. Geometry is everything that's visible. So every object that we placed before, every car, every road sign is a geometry inside the scene graph. Has a mesh. And as well, they assume this monkey face to be an object with a white material. Now they want to apply a different material. This is something we could do also with our cars. If we apply other materials, we could change the texture and the surface of these materials. What we did before with these boxes, so they were transparent. If you wouldn't apply any color, and we changed the material for the red box, for the green box, and for the blue box, in a similar way as it's shown here with the set material method. This is just for demonstration of possibilities of the JMonkey engine. Nodes is another interesting concept. We have spatial, which is a superclass of node and geometry. So nodes are spatials and geometry are spatials. And you can build a tree using nodes and geometries. We always start with a node. This is the root node, and you can attach further nodes or geometries to this root node. So we will see this. We assume this is a node, and we can use the method attach child, and any spatial, which might be a car, a traffic sign, anything, could be added to a node. Now we could also move it again. This is what we did before. Translate the monkey geometry one up. Move it. Now the node is now moved, not the geometry, so that we will see what will happen. The node, as it is attached to this child geometry, both will be changed. So you can use the notion of node to group several geometries to just one node, and this is the point where you can make the whole bunch of objects that you group to this node, you can move. So this is your handle for moving a large group of objects. So this is a really mighty way to have several nodes for several things in your world. So maybe one node is the scenery node. You attach all the static objects. You would have a car node that's able to move in your scenery. You add the wheels, you add everything that belongs to your car to that moving node. So you have different subgroups in your scene. What happens if you rotate a node? Well, the geometry, all the geometries that are attached will also move. Yeah, here you can see no longer the node is rotated. We just rotate the spatial back, and what happens? Only the spatial will be rotated. But remember, the node is still rotated by 90 degrees, and the spatial is rotated twice, so it has again its original orientation here. So now they are going all the way back. First node is rotated back. Same applies for scaling. Node, if we apply, I'm just went one step back. You can see they scaled the node to double its size. All detached children will also be scaled by this factor, and this results in the geometry and in the nodes of double size. So next, they now only use the spatial and scale it back by half. So the spatial will be back at the original size, but all the other elements contained in the node will have doubled in size. So these are nice games you could play with within your scene graph to manipulate all the objects. Next is how to organize such a scene graph. So this is what I tried to explain already. You start with a root node, and you could add two further nodes. For example, the right node, let's say this is our static scenario. You apply buildings, you attach everything that is static in our scenery, and left node could be the vehicle node. So you can see in here only this node is changed. It doesn't have any impact on nodes that are higher in the hierarchy, and only influences the nodes and geometries that are children of the node that we changed. Yeah, you see they also use the difference between immobile and mobile nodes. So this is how you can request nodes. You can just start from every time. You can start by the root node. If you want to have the blue car and you know the ID of the blue car, you could use this getChild method, and behind that you can specify the ID, and you will get returned this spatial with that ID. So this can be a node, or this can also be a geometry. If I want to know this is my geometry, which is called enemy, I can request on any node I like, which is higher in the hierarchy. For example, for world, here I can request method getChild, and I will immediately get a hook to this geometry. Yeah, then we have we will see this in more detail later on, what culling means. This is hiding and and presenting spatials. You can, without removing objects from your scene graph, you can make them visible or invisible as you would like them. And this is also possible in an automatized way. Here we have another example for scene graph, and let's set culhint to always, which makes the corresponding object invisible. And we select now house 1. We apply this culhint method, and house 1 should now be visible. So this is a very quick way to let objects appear or disappear. It's much much less resource consuming than removing it from the scene graph or reloading it from the hard disk. But it's more memory consuming of your RAM, because these objects are still loaded to your memory. So now it's set back to inherit, and the building is back again. If we select a node, then this will have impact to all its children. This node has 2 children, and if we apply the cull hint to make buildings objects invisible, both houses will disappear. Then, yeah, you can just change it of one object back, so you overwrite the inherited values. So you set this node to invisible, and by setting house 2 to visible again, the first value will be overwritten. Inherit returns it to the original position. If you set it to inherit, then you will have a behavior like that. All the objects that are in front of the viewing scene that could be perceived by the driver will be rendered, and as soon as they are out of sight, they will disappear. So this saves resources, as objects that you cannot see doesn't need to be rendered. Okay, this is already everything from this. Okay, now we're back in the slides. This is what we have already seen. We have a root node in our scene. Everything you implement with the JMonkey engine has a root node. You can attach any nodes and geometries you like in order to make them visible. Attaching anything to the root node by default lets the object appear in the rendering scene. Detaching it removes it again. And we always have this parent-child relationship, as we have seen from this previous demonstration. Okay, so the next concept is to get closer to the source code. There we will have a first exercise very soon. This is the structure of every application that has been created with the JMonkey engine. We have 3 important methods. So the first one is simple init app. Everything that is written there will be initialized at the very beginning. And the other one is simple update. This is performed several times per second every time the game loop is running. And any interaction, any updates to cars position or whatever updates in the physics simulation can be manipulated at that position. The third one is to create modifications with frame buffer, and is not necessary at all. So let's start with the first task. You can now go back to your environment, developer environment, and set up a new class there with the following settings. Okay, as most of the participants have made it to set up the Hello World, I'm going to follow this in my example. Here I just prepared another class with exactly the same code. It's just a different name here. And all we do is we are running a Java application. there are two there are two methods that need to be overwritten. Here it's only the simple init app, and the other one was the simple update. And if we just start the application, we will result in a black screen. Oh, sorry, it's also wrong. Just start it here and run it as Java application. So what happens is just we set up the simple application from the JMonkey engine. So as there's no object in the scene, we're not wondering why nothing is visible at this moment. You too should have in this tutorial package this class T01 hello GME3. You can now open this. It's the same code, and we can uncomment this part, which adds a box to our 3D space. So this box will have an extent of 1 meter in each direction. We add it as a new geometry. We add a color. So we first initialize material. Here you can select between different shaders. There's a predefined list that could be used. We will find this in the documentation of the JMonkey engine, but we still use the unshaded material here, and we can now assign colors. Here we assign blue, add this material to our box, and attach the box to the root node. If we run this example again, we will have a blue box in the empty space. So we can use the mouse to move around, or also the keys on your keyboard. So this is the point where we start from, and we are going to develop our own environment from this simple init app. So this is what we already did. As we have seen, there's a root node, and at the end of this example, we attach this blue box to the root node in order to make it appear. What we did, the box was not visible, and after this method, we can see it. In the same way, we can remove objects again. So in the last line, if we had this root node detached child blue box, we could remove it again, or using the method detach all children, and the scene would be empty again. We have 3 ways to ask for any spatials in our scene. The first one we have already seen from the previous presentation, where you could ask to get child. So the get child method plus the ID will result in the blue box if we would ask for the blue box there. All the objects in the node are enumerated. So we could also use this if we know the position. In our case, it would be the ID 0. For the first object, we could ask for get child 0, and we would also get the blue box. Or if you have access to the box, you could ask for the parent, and you will get the root node as a result. So here you see some explanation about the difference, again, between geometry and node. Geometries are visible as long as you don't say other, and nodes are always invisible. They are just used to group geometries and other bunches of nodes to one super node. Okay, so we start with the next task. I've prepared in this tutorial package another class which is called Hello Nodes, and it contains two boxes, not just the. Now we have another red one, which is exactly the same except of the color. And your task is now to add another node that's called pivot, and you should add this node to the root node and both of the boxes to this pivot node. So I go there too, and here's the space left empty. These two parts where you can do this task. It's just 2 lines. I show you the slide again with the required methods here. Okay. In the meanwhile, I showed you the solution to this task. I filled in these missing gaps. Here I attached this pivot point to the root nodes, and to have the red and the blue box attached to this common, this shared pivot point, I need another 2 lines to do so. And transitively, I attached the red and the blue one to the root node. So they are both direct childs of the pivot point, which in turn is a child of the root node. So also the red and the blue one are children of the root node. And here in the last line, I'm rotating only this pivot point. And if we start again, I think this is wrong. To start this one, then we should see 2 boxes which are both rotated, even if I just selected the node to be rotated. Okay, so let's proceed. Now we have seen that we can rotate objects in our scene graph, but as you already know, there are other kinds of transformations available: translation, scale, and rotation. And here's the methods that could be used for translation, where we have to distinguish between local translation, this is absolute translation, and relative translation. So in the first piece of code, you see how to set an object to an absolute position. We use this to set the spatial, which is called thing, to 0, 40, -2 in 3D coordinate space. And if we just want to move objects to set them to a relative position, we can use method that is called move, which makes the object 40 units higher and 2 more units to the back. Here in this table, you can see what happens if you change the x, y, and z coordinates for the translation, for the translation transformation. If you increase the first value, which is the x value, you move your object to the right. Decreasing moves the object to the left. And similar for the up axis, positive moving objects up, negative down. Z axis, which is facing towards you, leads to, when you increase this value, leads to objects coming closer to you. If you decrease this value, the object will disappear, will get further away from you. For scaling, this is simpler. There is no local scale. There we have also 3 values: the length, the height, and width, dependent on the axis. And last but not least, for rotation, there again we have 2 methods. One is called rotate, which adds some angle to the current orientation. And you can also set absolute rotation from the 0 rotation. This is done by using the set local rotation method. Yes, please. The question is, what's different between absolute and relative positions? Let me explain it with positions. It might be easier to understand. If you consider to have any object, maybe in this room, I have a pen now in my hand, and I apply the method set position, and I call this position door. Then this is an absolute position. I set this pen to door because I know that the door has any position in the room, and I apply this also to the pen in my hand. And relative position, to move it relatively, you have to know where this pen was before, and you add it. You say I add the pen 5 units to the left and 3 up. And for the absolute, you don't have to know where the pen was before. So here we have another table, which makes it maybe easier for you to understand what the 3 parameters of the rotate method mean. It's the rotation around the axis. So the first axis is the x-axis, which is going from left to right. And if you would think of axis in front of you, which is going from left to right, you could rotate objects that are fixed to this axis, and the only rotation around the x-axis which is possible is this, and this is like nodding your head. For the y-axis, which has this orientation, it's the up axis. The objects can only rotate around the up axis in this way, which is like shaking your head. And last but not least, the axis that is facing towards you, the only way you can rotate is like now we have the chance to look how we can apply these transformations. It's a little bit more visual stuff that is following now. For this reason, I provided you another Java class, which is called Hello Assets, in your tutorial package. This file contains three models and a light source. So the three models that are available can be seen in this small screenshot. There's this teapot on the wall with without any texture. We have a box, so we have this very simple model, and we apply a texture to this. You see these stones. And the third one is a complex model. That means we load the mesh files from the hard disk, and the texture is already contained. So these are three different approaches how we can set up models. By the way, is our recording running? Okay, very good. And in order to perceive and to see these objects, we have to place a light source. So let's have a look at the code. Let's go to the assets, hello assets file. I scroll down to the important parts. So in this section, the teapot is loaded. To remember, this is a complex model. That means we load the mesh file from the hard disk, and we have no specific texture. This is done here. We load the model from the hard disk. This is the position. By the way, we are loading a wavefront object file here. We apply a default material, which is provided by the JMonkey engine and could be used. We apply this to the teapot and add the teapot to the root node so that it is visible. So for the box, this is something we had done before in the previous tasks. It's a little bit larger than before. We apply unshaded material. What is new is we now set texture, which is a color map. So these are keywords, and you can't change them. There's a complete list of what is available in the documentation of the JMonkey engine, and we have to specify where the texture can be found that we want to apply to this box, let it appear like a brick. As we have seen before, we can set positions to all the objects, and this is the absolute position where we want the wall to be positioned. Last but not least, we have to attach it to root node, otherwise we would not be able to see that wall. Okay, this here is where you can get active. We are again loading a model from the hard disk. It's not in the wavefront object format. This time we are using the Opera XML. This is what we have seen before in the first tutorial. All the traffic signs and the model, the city model we were driving through, we had in this format. So what we do here, we load the mesh of this body, which we can see here. The texture is already contained, so we don't have to care about the texture. But when we start, so let me do this. When we start this for the first time, this model will not be visible because it's placed somewhere out. And that is your task. You see, the wall and teapot are already here, and you have to apply the following transformations to this body in order to make it appear at exactly that position with that orientation and that size. So you have seen on the slides before how to scale objects, how to rotate objects, and to set the translation. And this is now, I think it's a 5-minute task to apply these three methods: scaling, rotating, and translating the position of this body. So can do this here, and I would say in 3 minutes we can compare our results again. We go through together. I just paste here the solution, and then we can go together. So first, you were supposed to scale the body. This is done by the scaling method. You could do it in that way. You could scale all the dimensions individually, or there's another method. If all these values are the same, you can just provide only one parameter here. For rotating, there was a little pitfall. Rotating around the y-axis by 180 degrees, you have to convert here from degree into radians. So there's an easy way that there's a method that there's a parameter that provides this value for this conversion, and if you use ret to dec, it's the inverse to get it back. And last but not least, we apply a local translation by moving the object down and 2 units to the back. Perhaps you could also use move, as the initial position would be the origin, which is 0, 0, 0, and this would lead to, in that case, to the same result. So let's start and check what happened. Yeah, and now the linear is at that position. Can also move, use keys, WASD, if you want to walk around a little bit. It's rather slow here, but this is what the task should look like. So to make the scenery even nicer, yeah, this is a task I think we skip. It's just adding text to the rendering screen. I think if you're interested, you can try this at a later point of time. Let's do more visual stuff here. In the same way as we already added these 3 objects from before, we can add another model which is contained in your tutorial package. It is found at the given location in the scenes town main scene, and just try to load this model in the same way we loaded the other ones. And if you move it 5.2 units down, it will be positioned at the feet of this body. And you have to double the size of it. Okay, so here's the solution. Again, we load a model from the hard disk. I call the town, apply some, here I just used what you used that before, the move method, which is totally irrelevant, with which you both use when you introduce a model to the scene, and I scale it by the factor of 2. And you may not forget to attach it to a root node, and otherwise you can't see it. Running the simulator again should result in, yeah, same model with the town around us. So you see there are dark spots. This is because the light that we are using is not sufficient in these areas. And you see that the sky texture is missing. So this is the next thing we do. In the JMonkey engine, we have 2 different ways to simulate the sky. In the simulator, in the OpenDS, we had a chance to also to apply sky texture, And here you will see what happens inside the JMonkey engine with the texture you specify. So this texture is passed to the internal Sky factory, and you can distinguish between two different modes. The one that we have seen before was Skybox. That means it's a large cube with six sides, and textures are applied to all of these sides. You have to make sure that there are smooth transitions. So as you can see, this is an unrolled cube in the picture on the left. And the other approach is to have a sky dome or sky sphere, where you have texture that is wrapped around the sphere. And in order to distinguish between them, this is why we have a third parameter at sky at the method create sky, which distinguishes between whether we are working on a sphere map, and you have to set it true, and if you're working on a cube map, you have to set it to false. By just adding this code that we see here and attaching this to the root node, you should result in an image like that. So we can try this. I just copy, I prepared it here. Let's set up the sky texture. I use the Sky Factory, and here's the target where I can find this texture. This is actually a container including 6 different sky texture images, and I set this parameter to false as it's a sky box and not a sky dome texture. It's the same here with the models. You have to add everything you want to have in your scene to the root node. And actually, you can see it here, sky is handled as spatial, as it is a box, and this box is fixed to the camera. So you will never be able to reach the end of the box, as the box is fixed to your camera and will move around. Yes, the big disadvantage of the sphere map is that it's not that easy to generate. So for the boxes, you can do this with a digital camera, and there's some stitching software available where you can make one large image out of this. To me, I think it's two different approaches, but I don't have any preference. If you have, it depends on your source. So you have different ways. I don't have any preference. The question was if both look equally good. This is something I'm not able to answer. It strongly depends on your sources. I think you would not be able to see it whether you are in a cube map or you are in a sphere map. When you're in the scene, I think you would not be able to distinguish. I'm not sure about that issue. The question was whether there is an issue in the computation power that is needed for both approaches.
No, I guess the difference is only provide 2 ways depending on the software that people are using. So if you used to use sphere generation software, go use the sphere. If you do stitching, go use the cube. It doesn't really matter. By the way, if you have a blue sky, you can pretty much as well use the sphere and don't do anything to the picture, so it doesn't matter. And also with certain cloud shapes, you would not even see the difference even if you don't like apply this warping before, because clouds are not sometimes not very well defined.
Okay, as I think everybody succeeded to set up the sky texture, we go on. Here's just another table showing supported file types of the JMonkey engine, and as well as OpenDS is built upon this engine, you can also use these file types for OpenDS. What we have already seen are different model files. So the first line represents the Ochre XML meshes, which have this .mesh.xml extension, and the scene files with the .scene extension. So this is what we get from exporting objects directly from Blender. We have seen that we previously loaded this teapot model, which was in the wavefront object format. So we have OBJ here. We support Blender from version 2.49 onwards. Textures may be there as JPEG, PNG, or GIF. For our sky texture, we had in the previous example DDS files. There are also these high dynamic range textures available. These could contain, for example, such a sphere map. TGA, PFM, yeah, these are just other texture files that are supported. We have a bitmap font and two kinds of audio files, WAV and OGG. Orbis are supported. Yes, this question? Yes, the question was if we can use blend files directly to import objects. I have to confess I don't have experience with blend files, but the JMonkey documentation says it is possible. In general, that's true. But even with the object format, we encountered problems, as in the past we tried to import object files directly, and there were gaps in our maps. They were missing polygons. We don't know why. Then we opened it with Blender, transformed it into the Ochre XML, and suddenly the gaps were filled. So the information is there, but there seems to be some problems with the object files. Yeah, this might be. Yeah, okay. You just wanted to add that in the new version that this problem might be solved. Okay, let's quickly go through lighting. I want to let you know that there are 4 different light sources available. It's point light, direction light, spotlight, and ambient light. And they can also be handled like spatials, so that means you can place these light sources anywhere you like. You can control the intensity of each light source. And yeah, here we have some examples. Point light has some location and radius. So this is the range where you can perceive this light. And the farther you get away from the light source, the darker the intensity decreases with increasing distance. Typical examples would be a light bulb, a candle, or anything like that. Here's just how it is introduced to the source code. At the end, you see it's like just like spatial, also added to the root node when you want to have point light in your scene. It's very similar with the directional light. The only difference is it doesn't have position, as it has only a direction. This is to simulate infinitely far away light, such as sunlight, which has the same direction in any point of your map, and therefore you won't need a position. And as it would be rather unusual if you drove away and the sun would get would decrease in intensity.
Can you perhaps comment on the actual vector specification? So what does the vector mean?
The vector for direction shows us can be used to specify from what angle the sunlight is coming to illuminate our scenery. In this very special example that we see down here, this means starting from the origin, the start point of our vector is half a unit to the left, half a unit down, and half a unit back from us. And if you connect this final point with the origin, you will get the direction this vector is facing to, which is needed to describe how where the directional light emanates from. I hope this is what you wanted to know.
It's also, maybe we could also say at this point that the actual numbers are parameters in the scene file, just to loop back to what we had in the morning, that the scene file contains the numbers that form this vector if you create a directional light there.
Yeah, that's right. Yeah, and here we have spotlight, which is just some special point light. It has also direction and a position, and additionally, it has 2 angles and radius, of course, for the intensity, the range. These 2 angles, they are used as central maximum of the light cone and as the edge of the light cone. So this means where this dark spot that you can see here, you can let's assume that the point light is somewhere at the top of this sign, and what makes this point light to a spotlight is that there is a defined angle in which this light is perceived on the ground or on these objects that are inside the light cone. So if you enlarge this angle, there would be more area on the surface which is illuminated. Yeah, this is what you can see here. Everything outside the light cone angles will not be affected by the light. As an example, here you have flashlight. Yeah, it's rather the same. Here you can specify some parameters and add it to the root node. So ambient light is something different. You can also add it to the root node and set a color with intensity, but it influences the brightness globally. So if you set ambient light to some value, for example, if you set it to red, all the objects in the scene will have some red touch. Okay, so here's just an example on how to place a point light. So I add a new point light at that position. You can specify the color. In our example, we just have chosen red. You can set the radius. So if you are in a distance of 100 meters away, you won't be able to perceive this red light anymore. But if you are closer, the closer you get, the brighter the light will be perceived. And we set an absolute position very close to the origin, and we may not forget to add it to the root node. If we start now again, the result should look like in the screenshot. Yeah, I think there's somewhere the center of this point light, and you see the farther you get away, there's no light visible. Yes, please. Yes, shadow was not installed in here. We have just this small example. Shadow rendering is not part of our example here. Okay. So just give me another 5 minutes. I want to introduce the second important concept. By now we have only investigated on the simple init app method, where we could place all the action that occurs at the very beginning when you start your game, and we didn't have anything moving in the examples we have seen so far. And if you want to get some action into it, you have to place it in the simple update method, which is part of every simple application inherited class. So I'd also skip this task here and show you what I mean. So this is again back to the very beginning. It's a very basic example. You can see from the Hello World example at the start of the second tutorial. We again have this blue box, and we added the blue box to the root node. So I just run this as a Java application, and it's the same what we have seen before, just this blue box. And now I just want to show you why we have this simple update. This method is called while the game is running all the time in such a rate as can be shown as the frame rate. So if you have a frame rate of 50, this loop will be executed 50 times per second. And to get some action in here, it's just one line I want to add. So we want to rotate our cube. So this method is called multiple times, and we rotate our this cube around the up axis. So what you see here, this TPF, this means time per frame. So this is a number of milliseconds. The unit is actually seconds, so it's a number 0.000001. It's a very small number. And if you add all time per frame values of 1 second of your frame rate, then you will get exactly 1 second. So that means while 1 second elapsed, I rotated my box around this value. So then this concept makes the rotation independent from your computer speed. You can run it on slow machines, on fast machines. The box will always rotate at the same speed, even if the frame rate is different. So this is why we use this here. And just let me show you what happens. Stuff I have to store. This was this question. Okay. So, and now it's rotating at the given speed. And of course, you could use this update method for everything you want to change during runtime. Okay, I would say this is a good point to stop. The things we are leaving out is about input handling, how you can assign joystick buttons, steering wheel buttons, how you can assign keys of your keyboard, mouse actions, and the backface, the view frustum culling, how to make objects visible and invisible. But if you're interested, I think you could work through by the help of the slides. These slides are also contained on the USB flash drives. Today, I think we won't make it in time. For that reason, I pass over to my colleague for a more interesting topic, how to establish data connections to OpenDS. Okay, so you can have my seat. This is Daniel Brown.
Hi everyone. I'm going to give you a brief overview over a new feature in OpenDS, a network interface that allows you to pass data to the simulator from another machine or another program and get data from the simulator. Yeah, you can imagine a lot of use cases for this. For example, you can do real-time monitoring for experiments, or use external hardware. You can grab information from a steering wheel in a real car, from a CAN bus, and pass these data to OpenDS. But it's work in progress. It's not finished yet. At the moment, the data you can get from this interface is all about the driving car. These are grouped in 3 different sections: interior informations, like the rotation of the steering wheel, the pedals; exterior informations like the lights, the state of the engine; fueling informations like how many gas you have left, or what's your consumption at the moment; and physical attributes like the speed, acceleration, and position in the map. So what is not implemented yet is the possibility to give data to OpenDS. Raphael already told you about the events, and you already see you can trigger them by boxes, and our aim is to make it possible to trigger these events via the network interface. And yes, as I already said, you can use the steering wheel of a real car, or you can use some external program to control cars that are not driven by an actual user. And yeah, there are a lot of other possibilities. Not yet. At the moment, you can only get information about the driving car. But later, it will be possible to get information about every object with the ID of the object. So it's socket-based communication. It supports multiple clients at one time. It uses an XML format for the communication. I will show you some examples, and you will find some examples on your USB stick. And one of the main features is you can subscribe for a single value or for a group of values, and then OpenDS will send you updates of this value periodically. Yeah, here's an example how the protocol works. So after the client is connected to the server, the client has to send a establish connection message, and in this message you can also already specify what the update interval should be, and every information or every message you send from the client to the server will be responded so that you know the server received the message. So this is a simple example where we only subscribe the speed for the speed of the car. You see this route, this vehicle physical attribute property speed. That's how you address the values. I will show you this in a minute, how it works. As response for the subscribe message, you will get a list of all your subscriptions. So if you have subscribed some other values before, they will be listed as well in this list. And yeah, then you get a subscribed values message with all the values you subscribed in the time you specified. Commands that are available so far is establish connection, abolish connection, get data schema that will give you a XML tree as response where all the values you can get from the simulator are listed. So it's you can create clients that are highly adaptive and can adapt to the values that are available at the moment. You can get your subscriptions, a list of all your subscriptions anytime, and you can manually push the server to send you the values of your subscribed variables, even if you don't have a periodical update. Get update interval and set update interval. You can set the time between two update messages. By with get value, you can get a single value you want, and then you can subscribe and unsubscribe. So these are two examples for the message format. As you can see, in the second message, it's also possible to send multiple comments in one message. For example, if you want to subscribe all values but one, you can send a subscribe for all values and an unsubscribe for the value you don't want in one message, or you can even mix. You can mix all events in one message. And how the data is addressed, the style is a little bit like XPath. You see, this is the XML tree you get if you send a get data schema comment, and yeah, you can address the values like this. So you can get a group of values, or you can get a single value. And if you subscribe for a value more than one time, you won't get it multiple times. You will only get every value only one time. So I'm going to show you how it looks like. So here you can see the interface is started at port 3519, and then we have some example client. We can start. So we are connected to OpenDS now, and where are the definitions? So these are the examples you also find on your USB stick, and with the example client we can just send one of them. So first we send a established connection message, and as you can see we immediately receive a connection established message. And now, for example, let's subscribe some value. So, for example, the speed. Yes, I think I have. Oh, yeah. Subscribe. And now we get these messages. The default update interval is 1 second. So as you can see, well, at the moment we are not moving. And now if we drive, you can see that we can get the speed. Yes, that's it. Yes. Yes, because the idea it developed from a project we did where we use the XML format, but we are thinking about give the user the possibility to specify the format of the message. So because we know it's a big overhead for if you just subscribe for one value, but it's yeah. Okay. Yeah. Yeah.
Other questions? I guess, thank you, Daniel. Raphael is coming back.
We're reaching the end. Yeah, this is, I think, also the last chance for general questions about tutorials today. I see only faces waiting for the end. No? Yeah?
So the tutorials today
Yes, the materials for today are already contained on your flash drive, and I got a request this morning to provide the slides of the introduction. These slides are not contained on the flash drive, but I will upload them, so you have every slides of today, and also the source code samples at hand. There's only one thing I could add: the solutions to the second tutorial was missing, but then you have everything.
Solutions are good.
Yes.